So hello everyone, thank you for coming to my talk on measures and mismeasures of algorithmic fairness. And so, a quick about me, according to the Google Cloud Vision API. So, I ran a picture of myself through the Google Cloud API, or the Vision API, this picture, and it said multiple things about me. So let's go through some of those. Dancer, yeah, that's pretty true. I'm an aerial dancer and a circus acrobat. I just moonlight as a data scientist for 40 hours a week. Gotta pay that rent somehow. Am I entertaining? Hopefully, you're stuck in here with me for the next 40 minutes. Am I fun? Most of the time. And what about this one? Am I a girl? So, this is not true. I'm a cis man, and I am also male presenting. I just realized that as I was saying this, that could be interpreted in a different way. But the point of this example is to show an example of bias in algorithms. Like, why did Google Cloud Vision think I am a girl? Well, that's because the data set it was trained on, when it looks at dancers, they're also primarily women. So at any time it recognizes, like, oh, this is an image of a dancer, it also assumes the person in the image is a woman. And this is not just true for Google Cloud. Like, Microsoft's computer vision API will basically say the same thing. It will say, like, oh, this is a lady. Or I have had one picture of me where it says, like, oh, this is an angel descending from heaven, which is technically wrong, but in spirit it's actually right. So what is algorithmic fairness? And I guess the goal of algorithmic fairness is that it's this growing field of research that aims to mitigate the effects of unwarranted bias or discrimination on people. And so, like, this is more than just regular misclassification. Okay, if you have a image recognition detector that tries to say if it's an animal is a cow or a horse, like, if it misrecognizes cows as horses, like, yeah, it's kind of bad, but there's no deep societal implications because of that. We really care about, like, unwarranted effects of discrimination on people. And so you might be asking yourself, like, well, isn't bias and discrimination the, like, entire basis of machine learning? And this is a kind of issue with this discussion because bias and discrimination are very overloaded terms. Like, I'd say that a second overloaded term compared to kernel, and kernel being the first one in, like, machine learning data science where it has, like, a bunch of different meanings. And algorithmic fairness is primarily focused on, like, creating mathematical formalisms of fairness. Like, we're going to take this mathematical definition of, like, this is what fairness is as this equation, and then we're going to come up with solutions for that mathematical equation. And so this is a problem I sort of have with, like, all this research. It's like, I think it's really good. I think it's great that people are talking about these issues. But the issue with solving these mathematical formalisms is that you can solve the mathematical formalism. You have this mathematical definition. You can solve it as some constraint optimization problem. But does that actually do something for the overarching societal, like, issue? Like, if you solve the math problem, are you solving the general problem that faces society? And I think it's important to keep in mind that fairness is inherently a social and ethical concept. And the thing about this is, like, what we consider to be fair changes with time. Whereas mathematical definitions sort of stay the same. And I think one thing to keep in mind is, like, so I guess this talk is really my criticism of, like, this over focus on, like, mathematical formalisms in algorithmic fairness. And I guess what do I want the takeaway from this talk to be? Like, what I would say be the underlying thesis. So to sort of, like, appropriate a quote from my favorite Mage Knight, I think the end goal of this talk should be that, like, in practice, as data scientists, we should be using more than just algorithms. We need to be thinking about ethics, and we need to think about anthropology as we go about our work. We can't just, like, try to solve this as, like, an algorithmic or computer science problem. Like, that's very text solution-y. Like, oh, we're just going to use math, and suddenly hundreds or thousands of years of racial and gender segregation or horrible effects will basically be overdone just by this mathematical algorithm. Like, that's very text solutionism, and that's not how this works. And I guess a general idea of, like, this research in fairness, accountability, and transparency in machine learning. This is the interdisciplinary research area that's working to make machine learning systems that work towards these goals. Like, traditionally, machine learning systems, they sort of just optimize parameters. They optimize accuracy. They optimize being right, getting the right labels. And they optimize these, like, mathematical objectives. But now we sort of want to create machine learning systems that can work towards more abstract goals, such as fairness and justice. And as a result, there's been lots of research in this field. Like, there's lots of papers on this. It was actually the keynote at the conference formerly known as NIPS last year. And it's become really popular. Like, there have been classes on this now, whereas, like, maybe 3-4 years ago, it was just, like, a very niche topic. And we're even having, like, a full, like, conference dedicated to this kind of research happening next January in Atlanta, Georgia. It's called the Fat Star Conference, representing, like, fairness, accountability, transparency, and machine learning. And also, it's just not researchers that's talking and caring about this. We're seeing algorithmic fairness and the impacts of algorithm in popular media. And so we have like several books such as Weapons of Math Destruction, Automating Equality, Algorithms of Oppression, name a more iconic trio, I'll wait, kind of thing, talking about the effects of like algorithms on different types of people. And I think this is important because like we're now seeing like what is the downstream effects of our work on the everyday person. Like when you're working at your job, you sort of just like work on making your models, meet your boss's requirements, get your paycheck, go home. Whereas now we're sort of talking about like what's the downstream effects of our models. Like yeah, you're not the immediately person causing the immediate harm to these people, but these harms are being promoted or enhanced because of your work. And I think this is important because like no one really wants to be the person who causes the apocalypse. No one wants to be the person who causes the attack up. Like even if you don't like consider yourself an ethicist and like, oh, I'm just a data scientist. It's not my job to like really be concerned with like downstream effects of what I do. I just like do my job. I just do stats and I do math and that's what I do. I think at the end, like no one wants to be these like the people being written about in these books. Like that's just like a terrible career move. Like, oh hey, I worked on this project. It's like, hey, isn't that the like terrible use of like computer algorithms? Like, no, that's not me. And so even if I can't convince you of like, you should care about algorithmic fairness from like a moral perspective, like we should just try to be good people, maybe I can at least convince you from like a legal perspective of, oh hey, we have these legal regulations in the United States in order to protect against disparate impact against vulnerable populations. So this is protecting people in education and employment based on race or gender or religion or place of origin, things of that nature. And so like, even if I can't convince you that you should care about fairness from a moral perspective, I can at least try to convince you that you care about this from you need to meet legal regulations so you don't get fired and lose your job perspective. And especially now with GDPR, so this is Global Data Protection Regulation. This is the reason why I received a bunch of emails in like April and May that are like, we've updated our terms and services, if you remember that. And so I think GDPR is an interesting step because like previously we've just had regulations for like specific fields like credit or housing. Whereas now GDPR is sort of like general protections on like any use case of data science or machine learning modeling of like, here are the regulations you need to meet and so that you prevent harm against people, and you also need to be able to explain like what your models are doing. Because people should be able to understand like these algorithms are like arbiters of your fate. They basically determine who gets a loan, who doesn't. And people don't understand how they're making that decision for them. And I think one cool aspect of GDPR is sort of making interpretability a requirement, that you have to be able to explain why your algorithm made a decision to an end user. So let's talk about types of algorithmic biases. And so it's like not just like algorithmic biases as like one giant vacuum. There's like ways you can sort of break it down. So the big problem we talk about is sort of like bias and allocation. This is really the most commonly researched family of algorithmic fairness. Like, this is why we invented all those mathematical definitions that I'm going to like talk smack about later on. And basically the idea is like, how do your algorithms and models perform in binary classification problems or like multi-classification problems, just like supervised learning across different demographic groups? So how does it perform on men versus women? How does it perform on people based on race, based on religion, and based on place of origin, things of that nature, skin color? And the general idea is that like when we're allocating these finite resources, so like who gets a loan, who doesn't, who gets a job, who doesn't, we sort of often favor the privileged class over the more vulnerable. And that's just like years and centuries of like systemic inequality being aggregated into these data sets. And so when you train these models on these biased or tainted data sets, the models inherit those biases as well. And so for example, there was a big story last month where Amazon had to scrape their like AI recruiting tool because it showed bias against women. It basically, because of like the internal structure of Amazon's company, like, okay, they primarily had men. If you analyze the resumes of all the people who are in Amazon, you sort of learn these factors that secretly identify you as being men, like having a name like Jared, or like say being a lacrosse player, looking at, I guess, hobbies as well. And this is like I said, this is why we have all the math stuff. This is what we are now, and like we're actually trying to solve. Next problem is sort of bias and representation. This is like the harder problem, and this is like sort of where the field is sort of going, but we're still struggling with this a bit. And sort of looking at how harmful labels or representations are propagated. So you might have seen this picture before. It's like a very big story that when like Google Photos was first released, they had this incident where they accidentally labeled these group of black kids at a graduation party as gorillas. And so this is really, really bad. This isn't just like, oh, your algorithm made a misclassification. This is you made a huge misclassification that like ties into years of like racial bias and basically ties into like this racial slur against African Americans in the United States. And the issue with this is like it's often related to like these language and computer vision problems. These are like the neural network problems. Like we don't understand why, like what specific thing about this made it say gorilla, because these neural networks are very hard to interpret, kind of thing. And it's really hard to quantify this error compared to like bias and allocations. Like looking at who gets a loan, who doesn't, you can sort of like formally measure the counts of like who got a loan, who didn't. Whereas like with representation, like Google Photos is really never going to say like a white person as a gorilla kind of thing. Like it's never going to make that mistake. And bias and representation just goes beyond like misclassifications like this. It's sort of concerned with promoting harmful stereotypes or lack of recognition. So for example, like Snapchat filters, when you do these Snapchat filters, they also brighten your skin. And this is because of like when you look at like things like hot or not, we sort of believe like fairer, lighter skin to be more beautiful. Therefore, when these Snapchat filters are trying to make you more pretty for social media, they also brighten your skin. And so that's like, it's doing the optimization it's meant to do properly, but we sort of inherently feel that something wrong about this. Like this is not right, and this is not ideal. We want our algorithms propagating. And the same idea with language translation as well. So this is translating from a gender-neutral language of Malay into English. And we see that's like pretty much the same sentence structure, but we sort of have these jobs being gendered. Like he's a doctor, he's a soldier, he's a professor. These are sort of like male jobs, whereas she is a prostitute, she is a nurse, and she's a maid. These are sort of female jobs. We sort of learn that, okay, we have these jobs, and we sort of believe that these are masculine jobs and these are feminine jobs. And so it's also promoting these like harmful stereotypes that we don't want to promote. And the thing about this is interesting, because as I was doing a run-through of this talk with a friend, she's like wondering, like, does this actually still happen? And so I actually did test this yesterday night, and yeah, it actually still does, like this translation like this. Like if you actually put in the sentence like, he is a prostitute, translate it to Malay, and then translate that back, you get back, she is a prostitute, kind of thing. And next is the weaponization of machine learning. And so I think this is an interesting thing, that like this is where we need to be. And so as data scientists, we're not really taught about how our models could be used inappropriately. And so there was this big story last year where some Stanford researchers basically created a face recognition or face detection algorithm that basically tries to predict your sexual orientation based on your facial features or your facial landmarks. So, I mean, in addition to like just promoting shoddy science about like face phylogeny, this has caused a huge issue. Why? Because there are countries in the world where homosexuality is punishable to death by the state. Like in these like 10 or 11 countries, if you are like outed as a homosexual, you'll be executed by the state. So you can see if this model was deployed and make it publicly available, someone could take this and like out people as homosexuals in these countries. And that would put them in huge danger. And the thing about this is like, there's no mathematical optimization or statistical method that's going to tell you that this is a bad idea. Like there's no mathematical formula that says like, this is stupid, you shouldn't do this. And this is why I feel like in this discussion of like algorithmic fairness, you can't really just look for tech solutions. You need to bring in ethicists, you need to bring in anthropologists. And so I'm really glad as we're developing like, these data science and AI programs at like Berkeley or Carnegie Mellon or possibly at JMU. Yeah, I got you. That we are including an ethics components to this. Because we really need to think about like, how could these algorithms be misused by people who are not us? And like, this is becoming increasingly important because like, AI is being used in high-stakes situations now. So this is like police using Amazon face recognition in order to like, identify criminals. Like, okay, we have this picture of this criminal from like security footage. Can we just like take pictures of people off the street and sort of match them together? And that's how it's being used. But you don't realize that like, oh hey, Amazon face recognition, one, can be wrong, and two, is wrong more often on certain groups of people than other. And so this is going to be about like the types of fairness measures. So when we're talking about bias of allocation, how do you actually measure that bias? And so this is going to be based, like the mathematical notation I use here is based off a paper called Measures and Mismeasures of Fairness, of which is the inspiration for the title of this talk. And this has been done out of two researchers at Stanford, Sam Corbett-Davies and Sherrod Goyle. And so let's talk about definitions of algorithmic fairness. So there was like a nice talk like earlier in February this year by a Princeton professor, Arvind Narayan, about like how there are 21 definitions of algorithmic fairness. And I guess now there's more than like 30 definitions of algorithmic fairness in the literature. How am I doing on time? Perfect. And the key thing is like, okay, you hear there's 30 definitions. There's got to be some definitions that are better than the other, right? Like there has to be this like one better definition or this one true definition of fairness. And spoiler alert, there's not. Why? Because fairness in itself is inherently this social and like ethical concept. It's this cultural thing. Like what we define as fair differs across culture. And so you can't really narrow down like hundreds of years of centuries of like ethical and social like pondering of what should be truly fair, how we should orchestrate our societies, into like one quick mathematical definition. However, of these 30 definitions, we can really break them down into like 3 big families: anti-classification, classification parity, and finally calibration. So let's talk about anti-classification. And so this is sort of the idea that, okay, when we have our data set, we have our features X, we have some protected features and we have some unprotected features. So protected features are like your protected demographics. These are your race, these are your sex, these are your gender, these are your religious orientation, these are your place of origins. And the heuristic behind anti-classification is that your algorithm should ignore these features. And the thing we learned recently as we were doing this kind of work is that's not just enough to like remove those features from your training set. You can't just like drop those columns and then feed that data through your model and boom, boom, I'm done. We're no longer using race and gender. We're safe now. What we've learned is that you can accidentally learn proxy features. And so this is a very famous story of Staples, like the office supply company. They did this promotion of, oh, hey, if you live within 20 feet of our competitors, we're going to give you a huge special discount in order to incentivize you to come to our stores. Well, the thing about that is, so it's based on location. How they're sort of like doing who gets this promotion or not is based on where you live. The thing is, where you live, what neighborhood you live in, is sort of tied into your socioeconomic status. There are higher income neighborhoods, there are lower income neighborhoods. And as you might expect, there's different racial demographics of who lives in those higher income neighborhoods versus who live in those lower income neighborhoods. So by doing your classification or your discrimination based on location, you've accidentally learned this proxy for race. And as a result, you give these promotions to people predominantly white neighborhoods, and as a result, you don't give any promotions to people minority neighborhoods. And that's sort of basically acting the same as if you were to discriminate against race. And so Staples was hit with a huge lawsuit because of this. And so when we talk about anti-classification now, we also try to prevent ourselves from learning these proxy features. And so this is a useful framework for thinking about defining like how we develop fairness-aware models. And so what is a fairness-aware model? So fairness-aware models is sort of like an extension of traditional machine learning. You have like decision trees, and we have neural networks. And they usually just take some features X and with some labels Y. But now we have this set of protected characteristics Z. And what we want to do is create a model that can predict our label well, but also doesn't accidentally learn to predict the protected characteristics. We don't want to learn a subset of features that are actually proxies for race or gender or things of that nature. And so, like for example, this is a fairness-aware GAN, GAN being a generative adversarial neural network. These are becoming very popular over the last couple of years. Basically, there are ways to generate like AI art, so like generating artwork using AI. There's also from like real, I guess, more formal like artworks to also generating like anime-style artwork, which I feel should be referred to as Ganime, but I've never seen anyone refer to it yet. Anyways, so how this works, like the fairness-aware GAN, is you basically have 2 networks that sort of compete with each other. One is the like traditional classifier. It basically has your data and has the labels. And I'm just trying to like learn what features best predict the label. And then the adversary, and I think this is like a really brilliant idea, is that the adversary is trying to take the outputs of the classifier and trying to predict the protected classes. So it's like, I'm going to take your results and see how well I can predict these protected classes. Because if I can take your results and predict the protected classes like race or gender or sex, then you've accidentally learned these proxies. And so this is what this optimization function does. This is the like formal loss function for it. And so there's really 2 big parts. One is basically, is this a good classifier or not? Is this actually learning the labels properly from the features? And in the red box. And then in the blue box, we have, are you accidentally learning those protected attributes? And so this is a trade-off between like getting good loss of like getting good accuracy on the labels, but penalizing for learning the protected attributes. And so if you like stare at this a bit and like look at it, it sort of reminds you of like regularization. So when you do like lasso regression or ridge regression, which is like the stereotype, I guess the traditional way we talk about regularization in machine learning education, it sort of looks like that, where it's like you want to minimize the loss function, but we penalize you if your model becomes too complex, if your model has like too high coefficients in terms of like ridge regression or lasso regression. It's sort of the same thing here. Like we want to learn a good classifier, but we want you to pay a penalty if you accidentally learn these protected attributes. And so this is sometimes referred to as the accuracy fairness trade-off. And I'm going to be completely honest, I hate the fact that this is referred to as a trade-off, because well, we kind of expect the accuracy to drop. If the test set and our training set is biased, then we also expect the labels of the test set to be biased. Like we expect the test set to have these societal biases in them. So we don't want to perfectly emulate the test set. We don't want to get perfect accuracy on the test set because we believe the test set is wrong. We believe the answer key is wrong. So we expect our accuracy to be lower because we want to deviate from this. And I guess also the reason I hate that's referred to as like a trade-off is because I feel like it plays into this idea that somehow promoting diversity is somehow suboptimal. And so, for example, like there's a company, Duolingo. They're sort of like an app that helps you learn different languages. And they just announced that like, oh, hey, we now have like 50% of our software engineers are women. And that's like, that's a really good thing. But then there's always like some moron on Twitter. It's like, hey, I got a brilliant idea. What if hiring people, instead of hiring people based on gender, what if we hire the most talented person for the job? And it sort of ties in this idea that like somehow by promoting diversity, you're somehow hiring less qualified or less optimal candidates. And that's not true at all. Like getting more diverse opinions, I think, is really good for machine learning. And I'm really glad that there are people like, let's say, Becoming a Data Scientist forum. Got both of you. Which is like who are working to basically encourage like people from non-traditional backgrounds to get interested in data science. I think like having those voices in the rooms is very useful because they sort of tell you when you're being stupid, which is very important. Yeah. And now, so what's the big danger of like relying too heavily on these anti-classification measures? So by removing the protected features, we ignore the underlying processes that affect these different groups. And so the key thing that came about is that fairness is a process property. Like, we want people to be treated fairly. When we look at these fairness metrics, and this is like something I'll be harping on as I go through the rest of the talk, is that these fairness metrics are sort of focused on making the outcomes equal. And that's two different things. And so like there's like, I guess when you talk to like people say like, oh, skin color doesn't matter, we all bleed the same. But the counter argument to that is like, yeah, but we don't bleed for the same reasons. And I guess like that's the same idea. Like, yeah, the outcome is the same, we all bleed the same, but the process governing it is different. And so we ignore that process, you could accidentally hurt people. So for example, when we talk about prison recidivism, so this is basically you have prisoners and you decide like what's the likelihood they're going to reoffend? Like if we release them, are they going to commit a crime again and get back in prison? Because if they do that, we don't really want to like release them right now. And so when you look at prison recidivism scores, basically you see is that like women and men or female and male defendants, to keep the terminology right, is that women or females, so if you have the same score, so this is basically a risk score. Say this is basically what's the likelihood we believe you're going to offend as distilled in some number between 1 and 10, because people understand what number is between 1 and 10. Like I previously worked in cybersecurity, and I was taught like never convey risk as like, I try to just convey risk as like 1 to 100 scale because people understand that. We understand 100 is spooky, 1 is safe kind of thing. And so we display these, the potential of these people to reoffend as like this compass score. And we see is that for the same score, females have a lower likelihood of recidivism so that they are less likely to reoffend. But if you were to like ignore gender in this case, like you're trying to ignore gender or ignore sex in this case, and make everything equal, then you would sort of meet them in the middle. Like for a score of 7, we would say the defendants have a 50% chance of reoffending. And so the thing about that is that like that increases the likelihood of reoffend for females. And as a result, some females who would have been released on parole because they're at like 40% threshold will now be detained at the 50% threshold because we sort of ignore gender or ignore sex and thus push their risk up. And so by ignoring this, we sort of adversely affect females, and that's something we don't want to do. So next is classification parity. So classification parity is basically the idea that okay, we can't just ignore like race and gender and other protected characteristics. We want to see that our models do well across like traditional measures. So like accuracy, false positive rate, false negative rate. Is our measure like the same across these different protected groups? And this is what we usually use when we talk about when we like do our algorithms satisfy some legal regulation. Like when our algorithms in those regulated industries like banking or housing or I guess like equal employment. So like are you like unfairly hiring too many people of like white males, for example? Like we sort of audit those algorithms or those processes using like this type of metrics. And so here we have an example of some work by Joy Bulalami. She is a PhD student at MIT, and she does this project called Gender Shades, where she shows that like these commercial face classification algorithms do really poorly on darker skinned women, and so like it does really great on lighter skinned males, and does really good on like lighter skinned females, and does really good on like darker skinned males, but it's absolutely like not absolutely terrible, but like significantly worse on darker skinned females. And they show the largest gap, and so that's always just, in this example, like pretty much the worst versus the best. Like, what is that gap? And this is sort of how this like classification parity stuff looks at. Like, what is the gap between these metrics across different demographic groups? And so Joy's done a lot of work on this. She's actually done work that shows that like face recognition algorithms don't work on her because until she wears like a white mask. And she also has this really cool like spoken word video called like AI Ain't I a Woman, which she shows like how these commercial face recognition algorithms actually don't detect like famous women, black women, women of color. So like Michelle Obama, Serena Williams are not properly detected by these algorithms. Also historical women like Sojourner Truth also fail to be recognized by these algorithms. And so there are really two big ways we think about like classification parity. The first one is demographic parity. And this basically looks at the proportion of positive outcomes by the protected group. So if we're talking about who gets a loan or not, it's basically, is the likelihood of you getting a loan based on your race or your gender equal across all groups? And that's essentially what this mathematical formula at the top basically says. Like, I know math is kind of spooky, especially since I don't have like what everything means, but that's the general idea that mathematical formula is trying to convey, and it's based off the two Stanford research papers. I just took their notation. And basically, this is what we use to audit like models for disparate impact. We sort of follow this 80% rule. Like, is the probability of getting a loan given that you are a man, and the probability of getting a loan given that you're a woman, are they within like 20% of each other, kind of thing? Like, they have to be within 80% of each other. So that means like, are they off by at most like 20%? And the key thing is that this sounds simple. Like, okay, do we give loans at equal rates? Like, are we overly favoring one group over the other? And the thing about this is, you have to be careful because this is like an immediate constraint. And so if you can satisfy this and just satisfy this immediately, this is like short-term optimization. Like, you satisfy them now, but that can have potential consequences in the long run. And so to show this, there are some group of researchers at UC Berkeley, and they have this paper called Delayed Impact of Fair Machine Learning. And what they showed for like giving loans, for example, like you have the blue population, which is the minority population, the orange, which is the like majority population, and you want the percentage of loans to be given to both groups to be the same percentage. So like 60% of members of both groups get the loan. And the thing about, if you don't think about like credit loans, is that like if you give loans to people who can't pay them off, they're going to default. Like, they're going to like lose money because they have to pay back all the interest, and then their credit score is going to go down. So if you just want to satisfy this this constraint short term of like we have to make the number of loans we give between the orange population and the blue population the same, you might be giving too many like. You might give loans to people in the blue population who won't be able to pay them back. And as a result, they'll lose money, their credit score will go down, and overall, the credit score distribution of the blue population will go down. So if you just think about like satisfying the immediate thing without thinking about like long term, you can eventually hurt that population in the long run. Like, you can cause their credit scores to go down in the long run just because you satisfy the immediate need of like, we need to give about X many loans in order to satisfy this restraint. And you see this is like also in hiring, like going back to the example of hiring of like, oh hey, we need to get underrepresented groups into our company, and you sort of just meet that hiring process thing. But if you can't retain those people for like 6 months or a year because of something wrong with your company or your environment where it's like hostile to underrepresented groups, like, should you really get a pat on the back for that? Like, yeah, you're able to get people in, but you're not able to keep them in. And we're not thinking about the long term of like, how do we evaluate whether our company is good, like diversity inclusion wise. So next is parity of false positive rates. This is sometimes called equal opportunity. And as the name suggests, we're sort of looking at the false positive rates across different groups. So this is going back to like the gender shades thing. We want to see that our algorithm is doing equally well across all groups. And basically, like, it basically doesn't have to say, it has, we want to make sure that our error rate is sort of the same across all groups. Like, we don't want to be significantly worse on black women, for example, in face recognition than we are compared to white men. And the thing about this false positive rate is that it's possible to increase improve the false positive rate by increasing the number of true negatives. So for example, if you think about what false positive rate is, it's the number of false positives divided by the false positives plus true negative rate. So if you want to get that number down, because let's say you have like too many false positives for a underrepresented group, well, all you have to do is increase the true negatives. So what could that mean? So let's say for prison recidivism, so what is a false positive in this case? This would be detaining someone who would otherwise not go on to commit a crime or not reoffend. A true negative is releasing someone who does not go on to reoffend. So if you're like the chief of police officer or chief of police, and someone tells you, oh hey, your practices are sort of have like too high false positive rates, or your algorithm has too high false positives on a black man, for example, like you basically detain too many black men who would otherwise go on to not reoffend, you need to get this false positive rate down. What can you do? You can increase that true negative rate. So what does that mean? Is increase the number of black men who are released and they don't go on to commit another crime. So what does that mean? Go arrest more black men for like misdemeanors and low impact crimes, like go for drug possession of marijuana. Ta-da! We've made it fair now, right? No, absolutely not. And so if you don't really think about how this data is generated or the social process is generating that data, you could actually extremely harm those vulnerable populations. And the thing about this is this is widely used, and this has this huge oversight that, oh, hey, you just have to increase the number of true negatives. And so calibration. So calibration is like the last major family of like these fairness metrics. And so in risk assessment, so for example, like recidivism rates, and also child protective services, there's some true risk to the individual. Like if the child stays in this household, there's some risk that the child will be harmed. And we want to sort of estimate that true risk using some mathematical function S. And we basically say when this function is above our threshold, we're going to intervene or not. So for example, child protective services assigns a risk score to children. This is a score going from 1 to 20. 1 meaning the child is pretty safe in that household. 20 means the child is like in serious danger. Like this is a super high risk environment. And CPS intervenes if this like risk to the child is high enough. So with calibration, you calculate this score S, and the idea is that like once you have this score S, the outcome should be the same. So if you have two children who have the same like risk score, the likelihood of CPS intervening should be the same for both groups. So that means if you have a child with a risk score of 10 or a risk score of 15, two children, one black, one white, for example, because this is a huge issue where CPS intervenes more on black households than they do on white households, that if these two children have a score of 15, then the likelihood that CPS intervenes should be the same on both. It should be like 75%, for example, for both households. So what is wrong with statistical calibration? So you notice on the previous slides, I usually just had like a point at the bottom saying danger. Here's what the problem with this is. But I don't have this here because I got an entire new slide just dedicated to what's the problem with calibration. So the problem with calibration, how am I doing it? Okay, I got to speed this up a bit. Okay, debate about calibration. So this COMPAS, this is the prison recidivism algorithm. So this is the algorithm that determines like who we release on parole or not. And so it basically assigns this score to prisoners between 1 and 10. And so in 2016, ProPublica claimed that COMPAS basically, with black defendants, they have a higher false positive rate. They are detaining more with black defendants, they're sort of detained more often than they should be, who would otherwise go on to not commit a crime if they were released. And North Point's like, no, our risk scores are well calibrated by groups. And that basically means that, like, okay, if two people have the same risk score, so if you have these two individuals, and if they were to get the same risk score, they would both be detained if it was above, they would both be detained if they both have the same high risk score. The thing is, if the underlying distribution of the risk scores is not the same, like if we say like the risk scores, if it's above 8 or above, we're going to detain, and whites rarely ever get risk scores of 8 or above, but blacks get risk scores of 8 or above like half the time. Okay, yeah, it's equal. You're detaining when they're above 8, but the underlying distribution is not the same, and therefore you're going to detain more black men than you do white men. And so that's the issue with statistical calibration. Like, yeah, you treat everyone the same, but you don't acknowledge that the underlying distribution is different for these two groups. And I think this really goes to show that like you can optimize for one of these like metrics and horribly fail at one of these other metrics. And that's like a big result we're sort of learning now. There are like a bunch of papers about this. This is what this paper I'm basing this talk on was about. They're like, oh, hey, you really can't meet all these fairness metrics. Like in an ideal world, we could have like all the measures of fairness satisfied, but you can't do that. They're sort of like incompatible with one another. So I've talked about like what are these fairness metrics and so what are the problems with them. So what can we do to better improve like algorithmic fairness? Well, let's take a low-tech solution, or not low-tech, but low stats, low math solution. And how we're going to solve this problem? With better documentation. That thing you claim you should do, that everyone thinks you should do, but no one else to actually do. And so this is like really cool two really cool ideas. So first, it's called data sheets for data sets. And this was done by Timnit Gebru, she was at Microsoft's FATE group, Fairness, Accountability, Transparency, and Ethics in Machine Learning. And basically takes inspiration from safety standards and regulations in other industries. So like automobile testing or clinical drug trials, where we sort of realized that with automobile testing, they basically tested on prototypically like male-bodied dummies. And so these crash tests would pass it passed the crash test on these male dummies, but then you see that, oh, hey, women and children were horribly impacted by actual crashes because they didn't actually test for them. And same thing with drug trials, where we realize, okay, we're primarily testing on male participants, and so we don't actually understand the side effects on women or other groups as well. And so the thing like, I love about this data sheets for data sets is like there are a lot of talks about models, and like you read Medium posts about like different models and different algorithms all the time, but no one's really talking about like what makes a good training set. Like we just assume like there's some data, you grab the data from Kaggle or wherever you get your data from, and it's going to be fine. But no one talks about like what makes a good training set for a problem. And I think this is really like a first step in discussion of like what makes a good training set. Because like the training set is like the heart of this. Like if you have terrible data sets, if you have terrible ingredients, you're going to make a terrible dish no matter how good of a chef you are. If you have a terrible training data, you're going to have a terrible model no matter how good of a data scientist you are. And so this documentation really serves to standardize like the types of things we record about data sets. So like why was the data collected? Who funded its creation? Does it contain any like important sensitive information like PII? How was the data set pre-processed? And also, if the data relates to people, were they informed about how this data was going to be used? Because like informed consent is an important part of like any like research trial for social scientists. Yet somehow as computer scientists, when we do these A/B tests, we sort of get around this idea of getting informed consent around individuals. And so that's what I really like about this. It sort of standardizes, and like this is like, for example, is like a material safety data sheet. So it's like when chemists have like different chemicals, it says like all the properties of chemicals, like what is it? What is its chemical information, and also what are some hazards, and if you like things go wrong, how do you take care of yourself? First aid. And so like coming up with the same thing for this for data sets would be useful. Like this is a data set, this is what should be used for, and this is what you should not use it for at all. And the model cards are sort of like this analogous thing, but for machine learning models, like trained productionized models. Like let's have better documentation about how we think about machine learning models. And so this was Google researchers, and so this is when Timnit left Microsoft and joined Google's research group. They basically proposed a similar thing of like documentation standards for machine learning models. And so this includes things like intended use, like how should this data model be used in practice? How should it not be used? How was it evaluated against different demographic groups? And so this is taking the ideas of like, oh hey, automobiles were tested on like male dummies, but not on female dummies. Well, we need to think about that for our machine learning models. Like, was it tested on different groups based by gender, age, race, or skin type? I actually learned while I was doing this talk that there's actually a formal classification of different skin colors, so that was really cool. And also ethical concerns. So this is like, if this model was like doing what it was supposed to do, could this be misused by someone? And so this is tying into like that sexuality classifier. Or like I was also thinking about like when I was doing my About Me slide, like how could like face recognition, how does it affect trans individuals? Like could you accidentally out someone by using face recognition technology? And then also other caveats as well. And I guess finally, I'm going to give some quick shout outs to some organizations I think are really cool. And so as a quick note, I am from New York City. And so like these are sort of like New York-centric things. And so if there are like equivalent organizations in like the MVDA area, please let me know after this talk. So first is AI Now Institute. So this is a research institute out of NYU. And it focuses on the societal and cultural impacts of AI. So this is like now not trying to think about like fairness in machine learning and like protecting groups solely from that like tech solution of like math and algorithms, but also bringing in like the ethicist or the anthropologist when we talk about like how does AI affect society and how does it affect people. And they recently hosted a symposium, their annual symposium on ethics, organizing, and accountability, where they talk about things of like the history of scandals of like tech scandals this year, which is mostly just Facebook and Cambridge Analytica and a lot of the downstream things from that. Like last year was Uber, this year's Facebook. Who's going to be next year? I'm excited to find out. I hope it's Amazon. Shouldn't have said that. And so I think it's like a really cool like way to have conversations about like AI, not just from a mathematical perspective, but like the social perspective. Like when face recognition goes right, how could this be used? Because like face recognition is like someone takes a picture of you off the street without your knowledge, and boom, it's flashed through this classification algorithm, this recognition algorithm, and they can get a lot of information about you that you don't want people to get about you. So we need to think about that when we, like, as we further use face recognition technology in like all parts of like society. And next one is the Data for Good Exchange. And so this is a free annual conference every September in like Bloomberg's like New York City headquarters that brings together like data scientists, non-government organization leaders. So this is like nonprofits, and then also policymakers. And so if there's anything like this at in this area, like especially in DC, because I imagine I'd hope there is like some conference where you bring together like data scientists with policymakers, hopefully. And I think it's a really good way to have like a combination of like the theoretical research and then also like the best practices learned by policymakers. Whereas like the researchers are able to say like, oh, hey, you should implement this. The policymaker says, we tried to implement this research. Here's what actually happened in practice compared to like your theoretical results or your simulated results in your paper. I think it's a really good way to get more people into the room, just because like having different viewpoints when we talk about the effects of AI on people is important. And finally, I just have like all the papers I would sort of bring up during this talk. So like the measures and mismeasures of fairness, delayed impact of fair machine learning, the data sheets, model cards, agenda shades that I talked about throughout this talk. And so it's here in the last slide. I also have this paper that just came out pretty recently called Fairness Abstractions in Socio-Technical Systems. And this is sort of like the same spirit of this talk of like, oh, hey, there's a lot of work in this algorithmic fairness stuff. But they seem to fall into a lot of these like 6 common traps. And so they discuss like, what are those traps. And this includes like the focus on formalism. And so that's the end of my talk. And I hope you really enjoyed it.